Hello, everyone. This is our last set of notes for Unit 3. We're going to be spending some time talking about the half-life and the stability of these radioactive nuclear isotopes. And we've got a couple of labs that are going to give us some simulations, some visuals of these processes. But it's important to really take some time to just summarize and talk about the simple math and identification that we're going to use to be able to figure out these particular parameters for nuclear chemistry. All right, so half-life is always and foremost referring to time, and that's the time required for half of the radioactive material to decay. Okay, so some radioactive material decays very quickly, and it has a short half-life of a couple of seconds or a couple of minutes. And some radioactive material that's slightly more stable could have particularly long half-lives. You all are filled with radioactive carbon isotopes, carbon-14, and this is the one isotope that a lot of archaeologists and paleontologists will evaluate to determine how old a fossil is, because carbon-14 has a half-life of 5,715 years. So if your body has at least 1 gram of carbon-14 in it, 5,715 years later, it will have a half a gram of carbon-14. So since all living organisms are made out of carbon, and there are small trace amounts of carbon-14 in every fossil sample, they're able to do what's called radiocarbon dating to figure out how much carbon is left, and then evaluate roughly how old that sample is. Okay, so again, half-life refers to a length of time. That could be seconds, days, years, etc. And radioactive nuclides can undergo multiple half-lives, depending on how long the half-life is. So by comparing the mass of a starting sample to its final mass, you're able to figure out how many half-lives occurred. And then from that, you can figure out how old the sample is or how much you're going to have after a certain amount of half-lives have occurred. So if I started with 40 grams of sample and I then end with 20 grams, that's 1 half-life. And then if 20 grams goes down to 10 grams, that's a second half-life, and so on, third half-life, fourth half-life, all the way down to 5 half-lives. So each half-life length of time is the same. If this sample, 1 half-life was a year, it would take 5 years to go from 40 grams down to 1.25 grams. Okay, so by understanding the half-life, we can use radiocarbon dating to figure out how old it is, or again, determine how much of a sample will remain after a certain length of decay. So the actual practice of this is a little bit of just like a logic problem. I like to think outside the box questions that I've been asking you since the beginning of the school year. So it says phosphorus has a half-life of 12 days. So it takes 12 days for half of the phosphorus to disintegrate or decay. And they want to know how many milligrams of phosphorus remain after 36 days if you start with 4 milligrams. So there's no real equation to utilize here, but if we start with 4 milligrams and we cut down to half of that, 2 milligrams, the length of time that that takes is 12 days. Okay, if we go from 2 milligrams, cutting in half down to 1 milligram, that length of time again was another 12 days. And then if we go from 1 milligram in half down to 0.5 milligrams, that length of time again was another 12 days. In total, 12 plus 12 plus 12, that 4 milligrams down to 0.5 milligrams took the length of 36 days. So after 36 days, we would have only 0.5 milligrams of our sample remaining. Okay, so again, half-life refers to how long it takes for half of that material to decay, and the length of each half-life is the same amount of time. Okay, so let's put this into practice again. I would also encourage you maybe to pause the video and think about this question before you just jump into hearing me explain it. Whether or not you do that, that's on you. But polonium has a relatively short half-life of only 164 seconds. And they want to know how many seconds it would take for 8 grams to decay to 0.25 grams. And so if we start with 8 grams, we're going to cut that in half to 4 grams, which will cut in half to 2 grams, to 1 gram, to 0.5 grams, to 0.25 grams, our ending mass. So the trick here, not really a trick, the one thing you got to watch for is how many actual half-lives occurred. From 8 to 4, that's only 1 half-life. 4 to 2, second half-life, third, fourth, fifth. So we had 5 half-lives occurring, and each half-life was 164 seconds. So we would need to multiply 164 by 5 to get that it would take in total 820 seconds in order for 8 grams to decay down to 0.25 grams. Again, this indicating a substance that has a really quick, really short half-life, so that material doesn't last for very long. Right? Last example problem I want to leave you with is to determine how long the half-life would actually be. It says in 30 minutes, you've got 1.2 grams of argon decaying, and at the end of that 30 minutes, you have 0.15 grams remaining. What's the half-life? What's the duration of each halving for this sample of radioactive argon? Again, if you want, pause the video, maybe try this out, see if you got it, and then come back. Okay? If we start with 1.2 grams, half of that is going to decay down to 0.6 grams, which will decay down to 0.3 grams and decay down to 0.15 grams. So we've got 1 half-life, 2 half-lives, 3 half-lives, but in total, from 1.2 all the way to the very end, this took 30 minutes. So if we had 3 half-lives occurring throughout that entire 30 minutes, that means each half-life is only 10 minutes long. And so it takes 10 minutes for half of this radioactive argon to decay down to half of its original sample. Okay? That's all we're talking about in terms of half-life. The Skittles lab that you may or may not have completed yet gives us a nice visual of this process in action. Okay? The last thing we're going to talk about in this concept of nuclear chemistry is referred to as the band of stability. And there's a little bit of a graph down to the bottom right of the page. This is not something that you need to have memorized. This visual will be given to you on your Unit 3 test. So don't panic. Don't think like, oh my gosh, this is really throwing in a lot of stuff at the 0 hour. We're just going to utilize this graph to help us to determine whether or not a nucleus is going to be stable or unstable. Okay? So in terms of nuclear stability, we know this, but again, as nuclei get larger, it takes a greater number of neutrons to stabilize the nucleus. The larger the atom, the more protons that are there to potentially repel and push apart from each other, makes a nucleus more unstable, but the more neutrons that we have to kind of pack in between there helps to keep the nucleus stabilized. Okay, so of the first 300 isotopes, we've got this sequence over here in this graph to the right, and 157 of the first 300 isotopes, starting from hydrogen going on, 157 of them are stable when they've got an even number of protons and an even number of neutrons. Yeah, that's not a coincidence. Nature works really well in symmetry and in pairs. All right. So then the remaining 50 and 52 exist stable with at least an even number of neutrons but an odd number of protons, like this 50, or an even number of protons and an odd number of neutrons. So most of the stable occurring protons, most of the stable occurring atoms in nature have some even component to them. There's only 5 in existence that are stable that have 5 protons and 5 neutrons, and that's these 5 listed down here below. Everything else in nature that has an odd number of protons and an odd number of neutrons is considered to be unstable. Right? All right, so the graph is a visual that helps us to see where these stable nuclei exist. All these little blue dots that kind of form like a zigzag up here through the middle are where those even proton, even neutron isotopes are graphed out. Okay, this red line, starting at the origin, is where we've got, for every one proton, there's one neutron. And so we see as we go further up the graph, our stable region starts to go away from that 1-to-1 ratio, and it gets really closer to this green line, which is a 1 to 1.5 ratio, which means we have more neutrons than we do protons, more packing peanuts to help stabilize that proton nucleus. Okay? So the main thing that we want to focus on is that if we were given the number of protons and the number of neutrons within an atom, and it lands in this blue region, we can say that it's going to be a stable nucleus. If it lands outside the nucleus, outside of this band of stability, we can say that it's going to be unstable. Okay, so this is just a graph that helps us plot points to see where it's stable, where it's unstable. Okay, nuclei that land above the belt, if on our y-axis we've got neutrons and on x-axis we've got protons, if we land above the belt, then that means that the nucleus has too many neutrons. Okay? If we land below the belt, then our proton number is a little bit larger, and that means that nuclei have too many protons. And so what's going to happen to get these to be more stable? All of the atoms that land above the belt are going to undergo beta decay. If we recall from our last set of notes on nuclear chemistry, beta decay changes a neutron into a proton. So our atomic number increased every time a beta particle was released. Right? If we land below the belt of stability, this is where we get beta absorption, or what sometimes is referred to as electron capture. Okay? So we'll say, therefore, we'll undergo electron capture. And this was the nuclear decay, the fourth one on our last set of notes, that had the electron being added to the left side of the equation, and that took our atomic number and decreased it by 1, and that essentially converts a neutron or a proton into a neutron. So both of these decay processes cause the nucleus to change, and it changes up the ratio, leading it to be more stable and getting closer to that band of stability. Okay, so really what I want you to remember or understand is being able to plot where these nuclei occurred. Okay, we've got 20 protons and 35 neutrons. Clearly we're above that blue shaded region, so this is an unstable nucleus. Okay, if we've got 40 protons and 50 neutrons and we land inside that blue band, then clearly that has to be a stable nucleus. Okay? And you notice that the graph, if I clean up some of my work over here, it trails off and it stops right there. It's a terrible vertical line, but it stops right after 83, because there are no stable nuclei that have a number of protons greater than 83. After that, the nucleus just always becomes too unstable, and it undergoes one type of decay that we've already talked about, alpha decay, because that kicks off 2 protons and 2 neutrons to get it to a much more stabilized atomic number. The reason we stop at 83 or 82 really has to do with the size and the stability of the nucleus. Even though we're packing in more really tiny protons and really tiny neutrons, the nuclei do tend to get quite large and therefore more unstable. Okay, so we do need to understand that if we plot our points and land somewhere beyond that number of protons, then we're also going to be unstable and therefore are going to undergo alpha decay.